I am Ramesh, Assistant Professor, Department of EEE, M. Kumar College of Engineering, Karur. So today's session, solid state drives. So we are going to see the continuation of last session in synchronous motor drive, session number 2. Since last session, discussed about how to control the synchronous motor using self-control mode and separate control mode. So both mode will be used to control the speed of synchronous motor, but only difference. So in one mode, that means your self-control mode, there is required synchronous compensators. That means to handling the oscillations, we need to provide the damper winding. But in separate control, it is not required, so it not produce any oscillations while doing the control of the operations, speed control. So it is required. It is not required any damper winding. So then both the case, we have to measure the speed. We can give the feedback signal to the input, then we can generate the reference signal, that means firing pulses to the control unit, then we can able to achieve the desired speed control. So now the same method we are going to applicable through power electronics converters. So that means you can use the inverter circuit to control the synchronous motor in self-controlled mode. So normally, what is the next step? Load commutated thyristors. Okay. So normally commutations indicates turn on, turn off of thyristor, turn on and turn off of the thyristors. So it will be depends upon the line commutation and forced commutations. Then load commutation. Here load commutations, it indicates the voltage which is developed in the load side is used to turn off the thyristor pairs. So here load will be act as synchronous motors. So that induced EMF will be act as to turn off the thyristor pairs. So normally we know for any conversions we need two kind of converters based on the source side. Suppose you have source side DC, source side will be AC, then you need to convert DC, then again it will be converted to AC, then connected to the synchronous motor. So here the load side converter is 3-phase 6 pulse. So all we know that the converter will be operates less than 90 degree, the inverter mode operates more than 90 to 180 degree. So based on the firing signals only, we can able to understand which one acts as converter and which one is act as inverters. So you can check it here. So while coming for the converters, it will be operated in the both voltage and current and positive mode. But while operating the inverter mode, so voltage will be negative, current will be positive. So that means that your firing sequence is more than 90 to 180 degree, it will act as inverter mode. So suppose if the synchronous motor operates the leading power factor, then what happens in the thyristor pass, it will be commutated by the individual voltage available in the synchronous motor. So that will be called as load commutated thyristor. There is a commutation process. But the thyristor 3-phase line commutated converters are commutated by the supply voltages. So there is a difference between line commutation and load commutation. So triggering angle is measured is by the comparison of induced voltage in the same way by the comparison of supply voltage in the line commutated inverter. So what is the reason means? So we need to develop the voltage to control your synchronous motor for the converter side, but supply voltage it is not plays any role for the control your synchronous machines. So what are the firing sequence you can generate it based on the how much voltage you are applying in the supply side. So based on either you can increase or decrease the firing pulses to run your synchronous motors. Firing angle up in load side converters, the firing pulses is 90 degree, and will act as rectifier mode. So during that time the load voltage and current will be positive, but in firing angle is 90 to 180 degree, the load side converters it change to voltage is positive and current also positive. So voltage is negative and current is positive. So here is generally either load side or source side, whatever the general principle for the converters. So here source side converters is act as converter, the load side will act as inverters. At that time the source voltage is greater than load voltage, then this time there is no possibility to commutate by the load side, load converter voltage. So in this time the line commutated converters is act as to turn off the thyristor pairs. So whenever condition changes to the VDL is greater than VDS, at that time it will be run as to turn off your thyristor pairs. So already know that your motor will be acted as motoring operations possible, braking operations also possible. So for these durations, for these conditions, for these specified conditions, it will be act as motoring operations. So during the another changes, so source side will be act as inverter, then this will be act as source side is inverter and the load side will be converter, then it will be operated as load side converter or is to commutate the thyristor pairs, then it will be under the case of regenerative braking operations. During the regenerative braking operations, motor torque will be depends upon the difference between the voltage of source to load side. So then we need to find the commutation angle gamma, that is equivalent to beta L minus U. Here beta L represents load angle. So for the successful commutation of thyristors, so gamma must be omega minus omega into TQ. So here it represents, so omega represents the frequency of motor voltage in radian percent, TQ represents turn of thyristor of the turn of time of the thyristor pairs. So you can check it here, whatever the explanation previously I gave. So this was the block diagram, so power circuit diagram. So here this will be source side converters, then this will be load side converters. So based on the firing sequence, either may be operated as converter or inverters, or so on first sequence operations, first one, this will act as converter. At the time the source side firing angle will be 0 to 90 degree. So here it will act as inverters. At the time the firing will be 90 to 180 degree. So during that time VDL is greater than VDS is greater than VDL. So it will be line commutated converters, line commutated process of turn off the thyristor switches. During that time the voltage and current are positive nature. So this will be motoring operations. So during the another sequence, another set of operations, the load side will be act as converter, the source side act as inverter, then vice versa cases. So this time this voltage is greater than this VDS. At that time it will be more braking region, that means induction motor run as synchronous motor run as synchronous generator. So that voltage is used to turn off your the thyristor pairs. Then we are moved to how to control the synchronous motor by using constant margin angle control. So here this block diagram entirely represents how to control synchronous machines by using the measuring parameter from the synchronous machine parameters. So you can check it, this is synchronous motor. So here you are using one position encoder. This position encoder receives the speed of the signal. So from the speed of signal is feed to the field control. So this field control is used to adjust the field winding of synchronous motor. So already we know the synchronous motor, the stator is excited by the 3-phase supply, field is excited by the DC supply. So we need to provide the control voltage to match the speed of our synchronous speed with respect to field. So we need to change the parameters because the synchronous motor speed and synchronous both are same. So we need to do the according to the excitation for the field winding of synchronous machine. So you can do the control over the same case. Then field is required. Field control, actually here the DC supply, AC supply means the field control, the converters may be placed the role to convert AC into DC, then it voltage feeding to the field winding of synchronous machine. Here next one you can check it the block in synchronous machines. So you can check the circuit, you are having stator current and magnetizing current, and how to produce the flux lines, in how to control the flux lines over the synchronous machine control, then how to apply the flux field current in the synchronous machine. So everything will be calculated by the mathematically. So these are the block diagram represents equation 1, 2, 3, 4 R and 5 R. Everything will be mathematical representations converted into block diagram representations. So just need to feed the signals what are required for the particular block. So for need to find the firing the load angle. Okay, load angle, because when are coming for synchronous machine, it additionally places the load angle, decides the how much of reactive power supply are injected to the line. So because synchronous motor it will act as compensator, so it may be supplies this reactive power or inject the reactive power based on the load angle. So load angle you need to calculate from this formula. So for that whatever the terms phi is required, then IM is required, then IF is required. So wherever it is required to signal, now we can feeding to the this block indicated in the phi. So similarly here, so I need to develop the magnetizing current. So everything will be calculated by the measuring the parameters. Instead of giving the reference signal here, whatever the parameter is measured from the rotor position, that value is used to convert into required current. For example, the same speed is given to here, then reference speed will be set. From that we can able to generate the limit current. Then limit current heading the another one feedback signal from the DC link current before the load commutated inverters. So from that I generate the ID reference. So from the ID reference we are going to get this term. Then we are going to use the flux control unit. So from that we can able to produce the commutation angle, the commutation time. So then the same sequence will be reflected in the current controller. So from that is used to convert into firing pulses. The firing pulses is used to operate the control rectifier. The control rectifier does normally AC into DC conversions. So from the DC conversions, it will be a line load commutated inverters connected here. So this will be maintain the constant parameters. So that will be feeding to the inverter side. So now whatever the parameters will be established through a load angle and with respect to the frequency. So we can do the firing sequences. Then firing sequence excited to the load commutated inverters. So like that. So by measuring the single parameter speed across the rotor of synchronous machine using position encoder, we can measure the speed. Then everything will be calculated to control the index synchronous machine. So there is a constant margin angle control. The next one, so how to control the synchronous machine using VSI inverters. So in synchronous motor, so we need to achieve the constant speed control over the load changes. So in general, in synchronous motor is controlled by self control mode and separate control mode. In self control mode, so rotor position encoder has plays the major role to measure the speed of our machine. So from that we can provide the stator voltage in the synchronous machine. In separate control mode, the speed of the motor is determined by the external frequency by using crystal oscillator. So it will be open loop control mode. So in self control mode, it is behavior like commutatorless motor controlled mode. So it have better stability characteristics in both steady state and dynamic range. But while coming for the separate control, so it have the instability problem due to hunting the oscillations. So hunting means it provides the oscillations over the operating characteristics. So in normal VSI inverters operate in the 180-degree mode conduction. So and it requires the force commutation and load commutation does not able to provide the control over the synchronous machine, because if you want to operate 180-degree mode, so line voltage itself it is used to turn on or turn off the devices. So previously we have discussed load commutation and force commutation, how it will play a major role to turn on turn off the devices. But while coming for it to use the voltage source inverters, it does not require any commutation circuits additionally. So we have three combinations of variable frequency and variable voltage control for the synchronous motor using VSI inverters. So first one, so using square wave inverters, how to control the synchronous machine. Then PWM inverters, then chopper fed square wave inverters. So each and every case you have only some few advantages and drawbacks. So to work on that particular drawbacks, we are moving to one method to another. So you can check it here. First one, the synchronous motor is controlled by square wave inverters. So Arduino square wave inverters having 2 pulse only. So from the 2 pulse, so we need to control the voltage. It is difficult to appropriate level. So here the commutation may be difficult at very low loads with very low speeds. So to work on the, we are going for the PWM inverters. In PWM inverters, so PWM inverters based on the PWM techniques it will be operated. So then DC link voltage must be maintained as constant. So for that we are providing the standard capacitors so across the rectifier after the conversions. So the rectifiers are used to feeding the constant voltage to the inverters, but it have the overcome the drawback of square wave inverters like commutation failure at low speeds. So it is able to control the speed from zero speed to maximum speed range conversions. So square wave inverters it have commutation problem at low speeds. So to overcome the drawbacks, we are moving to the PWM inverters. Then how to control the VSA inverter? Using VSA inverter used to control the synchronous machine. It provides the following advantages. First one, reasonable efficiency. So non converter cost is high because we are going to use conversions from one point to another point, from first DC to AC, then DC to DC conversions possible may be used, but still now not we are going to discuss in hereafter. So based on the input supply nature, either DC or AC, we are going to convert DC into AC, DC into DC, then DC to AC. So everything will be possible. AC means AC into DC, then DC to DC, then you convert DC into AC. Like that we can, whatever combinations possible. Accordingly, you can choose the load system AC. We can convert the corresponding or alternate switching components to control the speed of induction machine, speed of synchronous machine. So here, warp loop control method may be possible to provide the stability problems at lower loads. So but in case of commutator-less mode, it is very stable. So PWM drive is better dynamic performance than square wave drive. So here the applications will be used for low and medium power ratings. So you can check it here, and this is a block diagram for representation of synchronous motor drive with the inverter circuit by using crystal oscillator in the self-controlled mode. So here the crystal oscillator produces the reference frequency. The same reference frequency are used to activate the phase control rectifier, then will be having voltage setting. So from that the LC is a filter, the DC link voltage will be feeding to the inverter unit. Then this operates the synchronous machine. Why this is mentioned here separately means, so in synchronous machine the field is excited by separate DC source. Then the second figure is indicates whatever we have discussed previous same, but here input will be AC nature, then our output will be used to diode rectifier, so it does not require any firing sequence. Then it will feeding to the LC filters, then it will be connected to the inverter unit. So the inverter unit will be controlled by the variable frequency and the variable voltage with respect to the signal received from the crystal oscillator. Then third figure, so additionally this will be closed loop operation. So here the speed will be measured, otherwise the rotor voltage, rotor position encoder are used to play the role to measure the parameter. So because armature voltage, induced voltage, it will be reference parameter maybe we have taken. So from that you can develop the frequency of operating the inverter unit. Then the same speed will be measured using sensors, otherwise takeover generators, whatever methods used to measure the speed you can use accordingly. Then you can say compare actual speed with reference to the set speed, then produce the error. The error will be converted into control signal, that means firing angle, then it will operate your phase control rectifiers. So this operation will be maintained up till the desired, achieve the desired characteristics in the synchronous machine. Then third one, then fourth one, here you can check it here with the same previous operations, only the difference you are replacing diode rectifier. Here as the speed we can measure either using your takeover generator or take position encoders we can use. Then from that we can get reference frequency and reference voltage to operate the inverters. So but here does not control any play role for the rectifier side. So everything will be controlled from the inverter itself. And then last figure, so here you can use the choppers to limit the voltage be providing to the inverter, square wave inverters. So here you can check it, this and this pair same except this part, that means chopper part. So how much voltage we need to feed the square inverters? So that will be decided by this thyristor combination of inducting pairs, because the thyristor decides how much we need to connect or remove from the line. So that voltage is given to the square wave inverter. By the way, you can able to control the speed of synchronous machine. So previously whatever the conversions takes place, this entry voltage will feeding to the inverters, but here you can check it, this chopper only decides, even though you are converting from AC into DC, This chopper only decides how much voltage will be feeding to the inverter unit. So this is a simple block diagram representation of voltage source inverter fed synchronous motor drive. The next concept, CSI fed synchronous motor drive system. So why are moving from voltage source into current source inverters? So it is possible to provide the force commutations better. Then we can able to adjust the speed range from 0 to base speed. Then cost of the inverters will be increases due to post commutation circuit. So because previously also we are using line commutation, force commutation. Okay, so based on wherever necessary you can choose the force commutations. So but here the force commutation plays the major role to turn off the devices. So the machine is operated at unity power factor, then the efficiency of the system is improved under the low to medium range of commutatorless mode operation. So among all the drives possible to invert synchronous motor, the load commutated inverters with synchronous motor is popular in commutatorless mode operations. So at low speeds, commuters should be assisted. So already we have discussed in low speeds it not produce that much voltage to commutate the thyristor pairs. So we can additionally provide the additional circuit to separately to turn off the thyristor pairs. So for that we are going to discuss three concepts. So how to turn off the thyristor pairs. So here the force commutation circuit is necessary only for the low speed size of the circuitry. It is relatively small. Yes, okay. Well, so we need to control the speed at very low condition. So at that time it plays the force commutation circuit. So first we can discuss CSI fed individual commutations very commonly used for the every circuit. So this is the individual commutations. So this will be, so you can check it here, the unity power factor load is operated, each thyristor pair is controlled by using individual thyristor pairs. Then it will be act as constant current source inverters by using the providing the inductor circuit across the source. Here each main thyristor is provided with the oscillator to commutation purpose. So here this is the converters, the thyristor rectifiers. So it will be converts from AC into DC. Then this the inductor pair used to maintain the constant current. Then this is a 6 set of thyristors available. Then another 6 sets of thyristors available. The voltage will be available from the synchronous motor providing with the commutating capacitors, which is to turn off the each thyristor pair for T1, T3, T5 and T4, T6, T6 too. Everything will be correspondingly commutated by using another set of thyristor pairs. So that it will be cost increases, then cost of complexity of the circuit will be increased more. So next one, and the force commutation at very low speed can be obtained by auxiliary thyristor pairs as act as fourth leg. Here each leg will be connected individual to the according to the thyristor pair. Instead of that we are going to use common leg, that will be act as fourth leg of the inverters. So commutating capacitor connected across the star point of the common point to the auxiliary thyristor to the synchronous motor winding terminals. So here once machine is achieved the desired speed control, desired speed achieved, then the fourth leg inverter removed from the circuit, then it will act as normal converter control of synchronous machine. So then the fourth leg will be cut off from the circuit. So this will be called as harmonic commutated inverters. You can check it figure. So already T1, T3, T5 already we know. Additionally you have two more pairs, that means fourth leg is available. So fourth leg is commonly connected to the synchronous machine windings. Then capacitor is connected to the common to the every pair. Then this capacitor voltage is used to turn off the thyristor pairs. So once the motor is pick up the rated speed, then fourth leg will be removed from the thyristor connections, the thyristor inverter connections. Then it will act as normal converters. So this kind of working principle is called as third harmonic commutated auxiliary synchronous current source inverters. The next one, artificial quenching technique are used to control the DC link current. Then you can able to achieve the desired speed control. So what are the principles we discussed previously? The line side converter and the source side converters So line side converter goes for rectification mode, then inversion mode, that will be changed. Then it will be current flow in the DC link current also changed. So by the way, we can able to control the speed of synchronous machine. So in this case, once the switchover takes place, incoming thyristor will be removed, then outgoing thyristor comes to contact in. So you can check it here. So here interruption, that is what is the interruption of the DC link current. This current flow through this DC link will be decided based on this thyristor circuit. So this thyristor decides how much current we need to flow here. So because here the vice versa operations, either this control in, this control in 2. So here based on the required operation, it may be at present this will act as inverter, this will act as converters. But based on the requirement, it may be operated as this will be converter, this may be operated as inverters. That are vice versa operations. So during this range, we need the current flow will be takes reverse flow. So that reverse flow does not affect over the control operations. So for that, we need to control the DC link energization. So that will be controlled by using thyristor pass. So in this method, at the instant when current 0 reaches, then it causes the conduction. At the end of commutation, when the DC link voltage changes to in sign, because once commutation switching takes place, then you can change the sign of the DC link voltage, because that only decides either we can go for forward motoring operation or reverse braking operations. So here in the control pulse for the required inverter and converter will be generated through rotor position encoder. So here artificial quenching is indicates meaning for how to adjust the current or voltage will be energized in the inductor. So through thyristor pass. The next principle, how to control the synchronous motor using cycloconverters. So already we have discussed cycloconverter will be used to change the constant variable frequency and variable voltage operations. So by using line voltage in the commutation thyristor of cycloconverters, we can able to adjust the frequency from 0 to 1/3 of input frequency range. So the speed control also is variable from 0 to 1/3 of base speed. So here you can check it. So this is the two directional operations. So either going for the motoring operation, braking operations. So during motoring operation, it inject take the supply from the line. During the braking operation, it supply to the supply line. So here hall control thyristor pass is available. So here ABC is the 3-phase sequence for the synchronous machine. Then rotor will be rotor speed will be measured by using position sensors. From that we are getting the speed. The same signal is given to the firing circuit. Then will be decides how to control the current in the 3-phase winding. Here the speed signal is available, then set speed available. By the way, you can able to control the adjustable parameters. So by the way, you can able to control the speed of machine. So because once current flow through the circuit will be changed, then flux will be changed, then flux changed, EMF changed, then you can able to control the speed of the machine. So what is the difference? What is the range of speed control for the cycloconverter fed induction synchronous machine? So up to 0 to 1/3 only is applicable. So from the base speed. So here the dual directional power flow is possible. So then next concept, power factor control. So because the power factor plays the major role for our AC machines, that only decides how much current flow we are taking from the supply line. So if you are taking the low power factor machine, then it will inject more amount of current, then it will be reflects to the more amount of losses. So whenever the manufacturer to design any machine, it will prefer to reach to higher power factor. Unity power factor at present it is more difficult to design. So near more or less we are going to the unity range, then you can extract the less current as comparatively other power factor loads. So the power factor will be decides how much current will be takes place in the machine. So how to control the power factor? By the control of the current flow, because current flow is the indirectly related with the power factor. So if I because the power factor calculator are used to measure the phase difference between the two phases. So power factor calculator will be indicates the phase difference between two phases, that we calculate the power factor, then we can command value of power factor is feed to the comparator. From that you can generate the error. That error is feeding to the controller. That controller will decide the phase control. That means how to change the firing pulses to the field rectifier. So here you can check it, you can clearly understand. So here this will be, inside will be rotor, outside will be stator. The stator will be excited by the DC AC supply through DC supply using inverters, but here AC is available nature. Suppose available nature means you can use the field rectifier. The field rectifier means that is control rectifier. It requires the firing pulses from the phase delay phase control unit, then will be converts the DC, then will feeding to the motor control. So this closed loop operation will be executed till your power factor calculator matches with the command value. So accordingly you can measure your current value from the line. The next one is PMAC drive with a 6 pulse rectifier. So PWM AC drive. So here the input 6 pulse rectifier used to produce the non-sinusoidal and current harmonics which flow back to the power system. So here rectifier unit is available, then DC link available, then filters, then SMBS available, then 3-phase circuit is available. So here PWM inverters will be act as to control the synchronous machine. So normally the BWM inverters PWM AC drive system used to control 3 individual phases. So this voltage feeding to our synchronous machine, so you can able to achieve the desired speed control over the machine. So that voltage available in the each phase is used to control the synchronous machine. So your freewheeling diode is used to control the current flow in the other sequence, that is during turn of time. If any negative current flow will takes place, then will be given to the diode circuits. Then BSI fed sinusoidal PMAC motor drives. So permanent magnet AC motor drives. So normally you can check it this figure. BSI inverters. The BSI inverters it will be used to control the sinusoidal PMAC motor. So PMAC motor we need AC supply, so inverters is feeding the supply to the machine, but DC is available. So to operate the inverters we are going to choose the firing pulses. So here T2, T5 and T3, T6 and T1, T4 is operated for the firing sequences of your inverters, voltage source inverters. So before that, so you can check it, this T2 and T5 is operated by for C phase, then T3 and T6 will operate for the B phase, and T1, T4 is operated for the A phase. So we need to produce the reference current. Okay, each phase you can have measurement current. So from that you can compare the current, from that you can produce the error. That error is converted into firing pulse unit. So here the phase A and phase B phase C current is measured, then from the speed is measured from the motor used to generate the magnetizing current and frequency. From that you can produce the reference current for the generator. So that means the phase A, phase B and phase C. So just you can use the position encoder with the speed sensors used to extract the speed value. So from this speed value is connected here. From that we generate the error. That error is to produce the IM current, then frequency reference value. From the two inputs it is produce the IA, IB and IC currents. So that will be given to firing pulse unit. Before that you are having the input feeding from supply lines. Supply lines means it will be extracted from the VSA inverters, not direct supply. The supply feeding from VSA inverters. So if any mismatches, you are not able to achieve the desired speed control, this firing pulse will be adjusted. So suppose here speed will be having some parameters, it produces the error, then it will produce the new signals, then it will be operated with the new inverter with the firing pulses, other set of firing pulses. Then we have other set of current flows and voltages in the stator terminal. So here for each and every changes we can measure. This open loop be removed from the closed loop, removed from the closed loop is converted into open loop. At the time of the firing pulse will be changed each others. This is the voltage source inverter fed PMAC motor drive. So in any kind of motors we need to control, we need to use power alternating components. The power alternating components require the firing pulses. So here VAC inverters, so here will be possibility for operate 180 degree mode and 120 degree mode of operation, whichever the necessary to compatibility we can choose according to the mode of operations. So here VAC inverters operated for the different set of firing sequences. Once the motor achieves the desired speed, this closed loop will be removed, then it will act as open loop system whenever the speed will matches each others with respect to the desired value. So these are the techniques which are used to control the synchronous machines. Thank you.